Guys, so for the notes and really what we'll do with these PowerPoint slides, I'm not going to talk you through word for word what's on every slide because that would be boring and take forever. I am going to hit on the high points. But what I would encourage you to do, since I'm not going to read through them word for word, is to make sure you are going back and kind of looking over them, making sure that you're getting all the information out. Obviously, if I think that there's important information on the slide, I'm going to talk about it. That might mean that I'll talk about a slide, the whole thing, and might read through it. That might mean some of these I'll just kind of skip over. So definitely hang on to these, use these. They are on Canvas for you. But I'm going to try to highlight some of the key points today as we take a look at Chapter 5, Section 2, which is our introduction to graphs. If you remember in 5.1, we kind of just looked at the idea of the problems we were going to be studying, so the idea of these street routing type problems. So we're going to kind of build up the basics of those today in 5.2, which starts with the idea of what is a graph. Well, there's basically two elements to a graph that are there. One of which is the vertices, the second of which is the edges of the graph. Now the vertices are the dots. So when you're taking a look at graphs, and in fact I think I shared with you guys a pretty common one was the house example that we looked at that looks something kind of like this. And so we put these dots on each of the vertices that I mentioned to you. In other words, there would be 5 vertices on this graph. In addition to that, there are a total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8 edges. So the edges are the lines that go between the vertices, whereas the vertices are the points that the edges are going in between. Now, just because two lines cross does not necessarily mean that there's a vertex there. Notice that where lines 6 and 7 cross, there is not a vertex between those two lines. So just kind of keep that in mind when you're looking at a picture of a graph, that those two basic elements are vertices and edges, and they'll be pretty clearly labeled for you and oftentimes given names. So let's kind of take a look at an example of that. So in this example, we've got our vertices, which are labeled A, B, C, D, E, and then we've got the edges that are between them. So the edges, when we list those off, we list them off between the two vertices that they are. So this line AB would correspond to this edge right here. And where we list off BC, that would correspond to this edge right here. Now, some other important information from that graph, and we'll take a look at it in just a moment. But notice that there are some important features that we need to talk about. One of those important features is what is called a loop. So when we talk about loops, what we're talking about is anytime we've got an edge which comes back around to that same vertex. So notice that at B, there is an edge which loops around and comes back to B. In fact, that's the only place where you can start at one vertex, follow an edge, and get back to it. Notice that D and C look a little bit different as well. In fact, we're going to talk about those right now. So while C and D are not a loop, because in order to be a loop, you'd have to be able to start at C and then end at C. And in either case, starting at C and ending at D, that's not the same. But these do have a special name. They are what are called multiple edges, or in this case, a double edge. So a multiple edges or double edges when you've got multiple edges which are between the same two vertices. In fact, those are the only two on this graph. Now, as we mentioned with the house example, sometimes edges are going to cross each other at incidental crossing points but aren't actually part of the graph itself. So as an example on this graph, notice that you've got this line from A to D and this line from E to B, which are crossing at this point right here, but there's no vertex there. And that's going to happen sometimes. So don't think that this point is a vertex, all right? Make sure that you understand that a vertex has to be clearly labeled as a point and has to be given a name. In this case, that means that these two lines or paths are crossing each other, but do not actually stop at a vertex. All right. Now, when we go to name edges, there's really no right or wrong way, at least right now, because there is no direction in between them. It's not as if there's directional arrows saying from A you have to go to B, and from B you have to loop around, and from B, then you go down to C. There's no kind of order that really matters. So when we want to maybe talk about an edge, like this edge from A to B, we can either call that AB or we can call that BA. Now, we're going to talk about two sets that are actually going to be part of your homework. So these are kind of the start of the homework problems, and they're pretty easy. The first is what's called a vertex set. So when we talk about a vertex set, that's just a list of all of the vertices for our graph. In other words, our vertex set V would be equal to A, B, C, D, E, F. Those would be all the vertices. When we list those off, we use V to say the vertex set, and then we use these curled brackets to list them off. So anytime we talk about a set will always have those curled brackets. It's our set notation, so make sure to use those when you're writing those out on the homework. Now, similar to a vertex set, but a little bit different, is what's called the edge set. So instead of it being called V for vertex, we call it E for edge. And what we do there is we just list off all of the different edges for our graph. So we listed off AB, so that would be this edge right here. AD would be this edge right here. BB, so when it has the same, that indicates a loop, so that would be this one right here. Then you've got BC, BE, CD, CD once again, since it was a multiple edge and listed twice, and then DE. So notice that CD appears twice in the edge list because there's two edges. You will only do that if there are two edges. So it's not as if you would list AB and then also list BA, because AB is the same as BA. But CD and CD are two different edges, so make sure you understand the difference between listing multiple edges versus just a single edge. So one example of where graphs can be used would be in Facebook. Obviously, this is something that Facebook does behind the scenes, but let's say that there was a group of friends. We could use a graph to indicate who is friends with who. In other words, if we were to look at, say, Betty, Betty is friends with Meg and Moose and Ginger and Reggie and Archie. But Betty is not friends with Veronica, since there is no path directly connecting her to Veronica. There's no edge there. And also, Betty technically would not be a friend of Jughead either, just because, again, there's no edge directly going from Betty to Jughead. I believe, actually, I don't know if this is true or not, my wife watches a show called Riverdale. I wonder if some of these are characters in that show. I don't know. All right. Now, with this next example, what we want to kind of see here is that there is a possibility of having isolated vertices. So this graph shows an example where we've got isolated vertices which have no edges. We won't see these too often, but just know that they are possible. So if we were to list off the vertex set for this, our vertex set would be the set A, B, C, D. But the problem is, if we were to try to list an edge set, there are no edges to list. And so we can do that one of two ways. We can either write it this way, where we just use the squiggled or curled brackets and don't write anything in there. Or we could just say that the edge set is the empty set, which is denoted with a circle with a line drawn through it. So either one of those would be okay to say what the edge set was for this example. OneNote has been a little bit particular today. Let me close out of it real quick. I apologize, guys. I don't know why it's been having so many issues, but let me just reopen it, and hopefully we'll get that ink to stay where it needs to go. All right. So now let's talk about how to draw pictures for our graphs. Obviously, there's a bunch of different combinations. Like if I were to just give you a vertex set, which said ADLR, and then an edge set right here, you could draw a lot of different pictures with that. In fact, I've got a couple examples down here for you. In fact, both of these show examples of graphs with the vertices that I mentioned above and the edges listed above. But notice that one of these is a lot easier to read than the other. In fact, this first one right here is a lot easier to read than is this second one. In fact, this is the graph for those that were in class. If you remember, this was the bridges of Koenigsberg example that we looked at in class on Wednesday would have been. So kind of interesting to see that once again. All right. So yeah, obviously the optional pictures, those are kind of talking about which one looks better. Obviously we said the first one. Let's see. On this slide, good stuff for you to read, but I'm not going to talk through it. Now, this slide is very important, guys. This is the formal definition of a graph. I would make sure that you've got this copied down somewhere in your notes or wherever you're writing these out. But a graph is a structure consisting of a set of objects, which is the vertex set, and a list describing how pairs of objects are related, which is the edge set. Now, relations among objects include the possibility of an object being related to itself, which would be a loop, as well as multiple relations between the same pair of objects, which is where we talked about multiple edges. So a graph basically brings together all of those components that we were talking about before. Make sure, guys, that this definition is written somewhere in your notes. This is super important. All right. Now, as far as terminology, every branch of math has its own particular definitions and jargon that goes with it. And in this case, what we are talking about is graph theory. Obviously, it's got quite a bit on its own. That's going to be what we'll be talking about over the next few sections and chapters, actually. Okay, so now let's talk about some more of the key features of our graphs. Real quick here, get rid of that. In fact, it's going to be a pain in the butt, isn't it? Okay. Let me go ahead, guys, and restart once again. Thank you for your patience. Feel free to fast forward a little bit in the video while this is happening. Wish that it wasn't so finicky today. Okay, so with adjacency, here is what we mean by two vertices are adjacent. We say that two vertices are adjacent if they are joined by an edge. So an example of that would be that vertex A is adjacent to vertex B because those are connected by this edge right here. We could also say that A is adjacent to C because, again, those are connected right here. However, we would not be able to say that D is adjacent to C. Now, we can get from D to C by going up to A and then down to C, but notice that there is no edge that directly connects D to C. So D and C would not be considered to be adjacent. So when we talk about adjacent vertices, we mean two vertices which are connected by an edge. Now, adjacency can also talk about edges. We say that two edges are adjacent if they share a common vertex. In other words, AB, this edge right here, would be adjacent to AC because they both share this vertex of A. We could also say that BF, this edge right here, is adjacent to BE, this edge right here, because again, they share this vertex of B. However, we would not be able to say that AB is adjacent to DE because they do not share a common vertex. An easy way to know if two edges are adjacent is there must be at least one letter that they share in common when we name them. For example, AB and BF, they both share a B. For AB and AD, they both share an A. But for AB and DE, they do not share any letters in common, so they do not share any vertices in common, so they would not be considered to be adjacent. So now let's talk about degree. In fact, we already did discuss degree a little bit in class on Tuesday with the house example, where again, remember we had this picture of the house that we drew, and we had our vertices, which we labeled right here. If we want to talk about the degree, we talked about the degree being the number of edges coming out of it. So we said that these bottom two vertices had a degree of 3, these had a degree of 4, and this vertex at the top had a degree of 2. So let's take a look at the degree for some of the vertices in our graph right here. For degree of A, it says that that is 3. That's because you have 1, 2, 3 edges coming out of it. For the degree of B, we say that's a 5 because for B we've got 1, 2, 3, 4, and 5 edges coming out of it. Notice that the edges from BC and BC do count for 2. Another one that's interesting to look at is this degree of E. Notice that the degree of E is actually 4 because there are 1, 2, 3, 4 edges coming out of it technically, which is that the loop counts twice towards the degree. So make sure that when you are listing out the degree of a vertex that you're being careful with loops especially and with multiple edges as well. Some other ones that aren't quite as interesting, notice that G and H both have a degree of 1. They're kind of dead ends, and so they only have 1 edge coming out of them. All right. So now, when we talk about degrees of a vertex, we also oftentimes like to label them as being even or odd. We said that that was important. Again, going back to that house example, the reason that it was important was in order to draw this house without picking up your pencil, you had to start at one of the 2 bottom vertices, and we noticed that they were both odd. So it's important to notice whether a vertex is even or odd. So for example, E, since it had 1, 2, 3, 4 as its degree, E would be considered an even vertex. In fact, there are only 2 even vertices on this entire graph. E is even and D is also even. So 1, 2 right here. The other 6, if you want to go through and check, are all odd. All right. So now let's get into kind of the meat of what we're talking about in this unit. We've got 2 different things that we are going to want to do. We're either going to want to find a path or we're going to want to find a circuit. Now both paths and circuits both describe trips along the edges. The difference between the two, a circuit is what's called a closed trip. In other words, the trip ends back at where you started. A path is more open. It doesn't have to have the starting and ending points be at the same spot. In fact, for a path, they have to be different. So a closed trip, if you were to have, let's say, these 3 edges right here, very simple graph, maybe let's just think about a triangle, then you could draw a circuit for this triangle by going from this vertex A to B, then from B to C, and then from C back to A. That would be considered a circuit. You would not be able to do that if you just had a graph that looked like this, where you had maybe D and E, because you'd be able to start at E, D, and go to E, but there's no way to go from E back to D, so this would be considered a circuit, whereas this would be considered a path. All right, so let's go ahead and take a look at some more examples of this here. In fact, let me go ahead and restart once again. Hopefully it'll restart fairly quickly here. I'll try to figure out what's going on and why that ink doesn't like to stay where it is. All right, so I believe where we left off, we were just getting ready to look at some examples of paths and circuits with our example that we've been taking a look at. So here is that figure 5-10 once again. If we were to want to find a path, one example of that is A, B, E, D. So if you were to follow that path, starting at A, you would go to B. Then from B, you would go to E. From E, you would go to D. This would be an example of a path because you're starting at A and ending at D. If you were to go one more edge from D back to A, then we could call it a circuit because then you're starting at A and then ending at A. But without that, A, B, E, D would just be considered to be a path. Now, the length, when we talk about of a path, is the number of edges that you travel throughout it. So by going from A to B, that's 1. From B to E, that's 2. And from E to D, that's 3. In other words, the length of that path, A, B, E, D, would be a length of 3. So let's talk about a few more paths and circuits. A, B, C, A, D, E. Let's take a look at it. So A to B, there's our first one. B to C, and it doesn't matter which one we pick, but there's our second. C to A, there's 3. A to D, there's 4. and D to E, there's 5. So that would be a path because, again, we started at A, ended at E, and it's a length of 5 going from A to E. Now notice that this went to the vertex A twice, and that's okay, just as long as no edge is being repeated. So you can't go on an edge more than once, kind of like our bridge example. You couldn't go over a bridge more than once, but it's okay to end up at a point more than once. Now another path that you could take to get from A to E would be A, B, C, B, E. Let's go ahead and see what that one looks like. So we've got A to B, it says first. So that would be right here. B to C, right here. C back to B would be right there. And then B over to E right there. That would be another path from A to E. Now this is only possible because there's 2 edges between B and C. Now notice that normally we wouldn't be able to go A to B and then B back to A, but when there's multiple edges, we're able to get that to work. All right, now let's take a look at some more. So A, C, B, E, E, D, that would be A to C, C to B, again, doesn't matter which one you pick, B to E, E back to E, so we're going to use the loop there, and then from E to D. So that would be a path of length 5, and one of the edges in the path is our loop. Now let's see an example of a path that wouldn't work. So in this next one, A to B, then from B to C, so far so good. C back to B, again, so far so good. But B back to A is a problem. We've already used that side twice. That's not going to work as a path because we can only travel AB once. All right, so another example of one that's not a path, I'll let you work through that one. But this one ends up not being a path because BC gets traveled through 3 times. First 2 passes are okay because you can go B to C, C to B, but there is not a third line connecting the 2, so you can't do the third one. Again, I'll let you kind of work through that one on your own to see where that problem is. So those are all paths. Let's talk about circuits. So circuits, remember you have to start and end at the same place. So if we were to go B to C, C to B, so if we start at B, B to C, C to B, we end back at B. That's a length of 2. We count lengths the same way for circuits as we do for paths. And that's a pretty short circuit. In fact, the shortest circuit that we could possibly find is E to E, which is only possible because it's a loop. A loop will always have a length of 1 for its circuit, and that's the only way to have a circuit of length 1 is that it would have to be a loop. All right. So now, a couple more key features of graphs. I know a lot to take in. Make sure that you are getting these definitions down somewhere because all of this is important. A lot of vocab, at least at the beginning. So a graph is considered connected if you can get from any vertex to another along a path. Basically, that means the graph is all in one piece, all right? So no matter where I pick, if I pick G and then just pick any other point E, I can always find a path from one vertex to the other. So no matter which 2 vertices I pick, if I wanted to instead pick A and let's say H, I could go from A to B, B to F, F to H. And that would work no matter which 2 vertices I pick. If that's the case, then we say that a graph is connected. Now, an example of a disconnected graph would be if we were to take our original graph and remove that one piece from B to F. That's a very important part of our graph. Because if it's not there, our graph is no longer connected. There's kind of these 2 components to our graph. Now if I try to go from G like I did before to E, I'd go from G to F, but now there's no way for me to get from this second component over to this first component to finish my path. So when that's the case, when you pick 2 vertices and can't get between them, that's what we call a disconnected graph. Now, like I mentioned, that point right here, or this edge from B to F, is super important. In fact, if we were to remove another edge, like the edge from F to G, now we've got 1, 2, 3 components of our graph. And now, if you notice, both of these were important because every time we removed one of those edges, we got a new component. When that's the case, we say, well, first off, let me go ahead and give you the definition of components. Components are basically the number of pieces for your graph. So when I've been saying components, what I mean is that this first part, A, B, C, D, E, is a component, and then F, G, H would be a second component. But there was a special edge that I was mentioning. Let me get to the definition for that. So that special definition for that line from B to F, that when we removed it became two different components, is what's called a bridge. So that was kind of our whole point, was removal of one edge from a graph. Definitely makes the graph disconnected when we remove B and F. When that's the case, it's called a bridge. However, if we were to look at the line AB, the edge AB, this would not be considered a bridge, because even if we got rid of that edge, our graph would still be connected. You'd still be able to get from any one point to another, so that would not be considered a bridge. Same with this loop from E to itself. Obviously, that is not a bridge, because if we got rid of it, everything would still be connected. So a bridge is an edge where if you remove it, the graph becomes disconnected. So for example, FH would be a bridge because if we removed that edge, then H would no longer be connected to the rest of our graph. There would be two components and it would be disconnected. So in total, there are three bridges. The first is BF, the second is FG, and the third is FH. All right. So now we get to what Euler has his namesake for in graph theory. We have what are called Euler paths and Euler circuits. An Euler path, and this is an important definition, so make sure you've got this copied down somewhere. But an Euler path is a connected graph that has a path which travels through all of the edges of the graph. Now, being that it's a path, edges can only be traveled once, just like in our bridges example for the Königsberg bridges that we looked at in class on Wednesday. Now, by definition, only a connected graph can have Euler paths because of course, if you have a disconnected graph, so you've got kind of 3 points over here and then another 2 points over here on a disconnected graph, obviously we're not going to be able to go through all of the edges of this graph. However, if we were to build a bridge and build an edge right here, we could have an Euler path because we would travel from here to here, from there to here, and then we could travel around each of the edges, arriving back at this vertex here. Now, just because two graphs are connected does not necessarily mean that they have an Euler path. An Euler circuit is similar, and again, I would recommend that you go ahead and copy this down as well. An Euler circuit has to go through all of the edges of a graph and end where it started. So a circuit, remember, you have to end at the same point you start at. For it to be an Euler circuit, you also have to go around all of the edges. So our graph over here that I drew would not have an Euler circuit because there would be no way to travel all the edges and end back up at a point. So some examples of this, obviously we've seen one important example, and I know that the ink's following along and we're almost done, so I'm not going to worry about restarting. But one example of an Euler path was the one that we saw with the house. Remember that if you started at one of your points down here at the bottom of your graph and continued, let's see, 1, 2, 3, 4, 5, 6, 7, and 8. We only traveled each side once. We were able to cover each of our edges, and we were able to find a path between those. So this graph would have an Euler path. However, it does not have an Euler circuit. In order to have an Euler circuit, we'd have to actually add a couple extra edges. If we were to do that below the house and draw in, cut an extra 2 edges, we actually would be able to find an Euler circuit. Where you start at F, and then with the addition of those extra 2, now we're able to go 9, 10, and then back where we started. Now, this graph below does not have an Euler path nor an Euler circuit. So if you take off the top 2 pieces of our house and the bottom 2 as well, we no longer have an Euler path nor an Euler circuit. Now, just by looking at it, you probably can't tell. You probably have to spend some time trying to find those before you'd be able to understand that there's not one in between those. And actually, in section 5.3, we're going to learn how you can tell without having to try all of the different options. Until then, guys, have a great rest of your day.